Okay, so greetings everyone and welcome back to the Advanced SQL course. I brought a cup of coffee with me, SC Freiburg, as to celebrate that we have reached the last video for chapter 2 in this series. I guess chapter 2 is one of the longer chapters in this course, but we are almost through it. There's only one thing I wanted to discuss with you. And that's a nice use case, a sample use case for the use of the SQL common table expression or the with queries. That will bind together some of the things that we've discussed in the recent videos, and it's a nice finish line that we can draw under the discussion of the items of chapter 2 of this course. And whenever in the SQL, whenever we will enter a discussion of a longer use case or a larger example, you will find that wrench symbol in the upper left corner of the slides to let you know that, hey, we are putting SQL to good use now. Okay, so in this case, it's an exploration of what you can do with a simple use case for with, and that use case comes from paleontology. So I don't have a degree in that particular science, but it makes sense to me when the colleagues say that from the shape of a dinosaur body, and in this case, by shape I mean the height-length ratio of the main body of the animal. So from that shape, you can deduce whether the animal was using 2 or 4 legs to move. So whether it's locomotion, the form of movement, was based on 2 or 4 legs. So we don't have videos or any other clues for these animals, but we can deduce their body shape, their height-length ratios from bones that have been found, and that clues you in, that gives you some hint on whether these animals have been 2 or 4 legged. Okay, so here's an example of that. I think it becomes obviously clear that there is some meat to this hypothesis, and even if there isn't, it's still a cool SQL use case. All right. So we want to use this correlation between height and length, this body shape ratio, to infer bipedality or quadrupedality for a species that we have found and whose bones we could measure, but we not know yet what their pedality was. So this could be an entry in our data set, and that says, hey, we found this particular species, the Gallimimus, for example, and these would be the height and length measurements for its main body, but we don't know whether it was using 2 or 4 legs. So in place of that question mark here, we would like to have a 2 or 4 that tells us, hey, you are a 2 or 4 legged animal. That would be ideal. The data set on which we will base this exploration is this. So we have now switched from the playground table to the prehistoric table when we were talking about grouping sets. Now we've arrived at the dinosaurs table. Okay, so you see that this is the collection of data that the paleontologists have found so far. This is a number of species or dinosaurs that they know about, and some of these you will probably recognize. I recognize some of these. As I told you, I love Jurassic Park, but most of these are complete gibberish to me. Okay, so be it. For some of these, we know how many legs they were used to locomote, to move. And we also know their height-length ratios. From that, from this data, I try to infer the form of locomotion for these entries in the table, where the form of locomotion is currently unknown to us. We know about height and length ratios, but we don't know about quadro or bipedality for these species where we have an entry of null here in the legs column. Okay, so the plan is very simple. We will investigate the data, the part of the data for which we have locomotion information, and then try to infer the typical or the average shape, the height to length ratio for the bipedal and for the quadrupedal animals. And that's actually quite simply done in SQL, so let's do that. This could be a query that performs just this job. We would iterate over all the dinosaurs, D, in that particular table. We would ignore all those entries for which we don't know the form of locomotion yet. So we would focus only on those animals for which such locomotion information has already been collected and verified. Then we would divide the animals into the four-legged and into the two-legged species, and that's easily done using a group by construct here. So a group by D legs will leave us with two groups, the two-legged and the four-legged animals. All right. And inside each of these groups separately, we would compute the body shape, the height to length ratio inside that group. And we would use average aggregation to find the typical shape that is shape ratio that is characteristic for this particular group. Okay, and yeah, that would lead to this temporary table. I call it bodies. Okay, so this is a characterization of the body shape for the two and four-legged dinosaurs. These would be the characteristic average height to length ratios inside these groups. Okay, so far so good. So let's switch over to the editor and then establish this dinosaurs table. We don't have it yet, so let's create the schema. Perfect. And then fill in all the sample data. Some of these rows, the rows at the bottom, you can see are incomplete, and yeah, we want to derive information about the locomotion for these entries, for exactly these entries. Okay, so insert all the stuff. Table dinosaurs, there you go. That's the data we are going to work with. All right. So the bodies query, you have seen that on the slide. I've already formulated that using with clause. So I prepared a common table expression here already. And that's for a good reason, because calculating the typical body shapes for the two and four-legged animals is only half the job. It's part of the job. It's an isolated, well-defined part of the job that we can do here and now, and then later rely on the temporary intermediate result that we've already been computed, namely table bodies of two columns, legs, and shape. This would be the intermediate result that we are computing. This is just the query from the slide, and as you can see below here, I've already appended. I have appended the further computation that we will be using to infer the type of locomotion for all these animals. But let's not do that right now. Let's simply write table bodies here and make that a complete common table expression already. This is already a complete table, common table expressions. It would allow us to just simply inspect what we have computed in this temporarily defined name bodies. It could be used for debugging. Maybe the whole query will be larger, but we will now want to check that the bodies part, this bodies temporary table, or already contains the right data. So this is what we are going to check here, and yeah, it looks good to me. 2 legs, 4 legs, they have distinct body shapes. That gives us some hope that we can use this to tell the animals apart. That's nice. Okay, so this part of the CTE already can stand on its own, and we will append the complex, the full query that can infer locomotion in due course. But let's switch back to the slides first. So what would be a possible plan? What would be a possible plan to follow and to infer locomotion from the original data and this temporary table bodies that we've already prepared? So the plan would be the following. And when I say plan here, You have already noticed that there is a different notion of plan in the database community. Whenever the DB2 folks or the DB internal folks speak of plans, they mean the output of the explain command. And that's perfectly fine. In the context of the advanced SQL lecture, we will quite often speak of plans, and this would be more like plans of attack or strategies that we are going to pursue to implement a particular problem, or to solve a particular problem rather. So plan has a somewhat polymorphic meaning in the context of database systems, but in this advanced SQL lecture, it will primarily refer to the plan of attack, the strategy that we're going to pursue in the next few minutes. And what would be the plan for the dinosaur body shapes query? Well, we would start out with the bodies part, and we would rely in the rest of the query, we would rely on the bodies table already present. The details of how this body table has been computed, what went into that, is actually not important at this particular point. We just rely on the bodies table to be present. Okay. Given that this table exists, the rest of the strategy is actually rather simple. We would iterate over all the dinosaurs D, so extract all the dinosaur data and would call one row D. If the locomotion for D is known, and for some of the rows, actually for most of the rows in our table, that's already the case, then we could just output and leave D as is. There is nothing to be inferred locomotion, the legs column is already non-null, everything done. It only gets complicated if the locomotion of row D is unknown, so that would be this part. So we would then compute the body shape for this particular dinosaur. So we would compute the height to length ratio. We can do that. And once we have that, we would look up in table bodies that entry B. There's only two entries there for the two-legged and the four-legged class of animals. We would look up that entry B, that whose shape entry comes closest to what we've just computed for D. That would be the body shape or the form of locomotion that we assign to D. And that's the final point of this query plan here. So compute the body shape, try to look it up, or try to find the closest matching entry in the already existing bodies table. Once we found that, we have found the form of locomotion that we hypothesize, and that is the form of locomotion that we would assign to D. And that would be our answer for this particular D for which locomotion was unknown before. That's the query plan. Quite simple, and it's actually rather simply expressed in SQL. That's nice to know. Okay, so let's go back to the editor. There we are. So we have already seen that part of the CTE, the preparatory part where we compute the bodies table. So let's not look at this now. It's done, and we would rather focus on the rest of the query plan. Okay, so if you recall, the query plan was talking about two cases. When a dinosaur is already recorded in a table with complete locomotion information, then that would be one part of the plan, one part of our strategy, and that part's actually implemented down below here as the right-hand side argument of the union all. You see my comment here below the line, the locomotion of dinosaur D is known. As the plan said, iterate over all the dinosaurs. I'll do that. Check whether the legs information, locomotion information is already known, and if it is, we just leave D as is. It will contribute as is to the result. Okay, so that would be one branch, one leg of the case distinction that we've made in our query plan. Of course, the other part of the case distinction is more interesting. We are iterating over all the dinosaurs D, and we will find a dinosaur for which the locomotion information is incomplete. And as you can see, these predicates make sure that the right-hand side of the union and the left-hand side of the union will contribute disjoint data to the overall result. No dinosaur will be represented twice in this result. Okay. Okay, so we have a dinosaur D for which locomotion information is not known. But what we can do is we can compute its height to length ratio, the body shape for D in a sense. This is cool. Okay, so we are using this in a subquery. As you can see, this is a subquery nested in the select clause. Nested in a select clause means that we expect this particular query in parentheses here to yield a scalar value. That's what we are computing in all other columns here in the select clause, and that's what we are expecting of the subquery here. We need a scalar here. We can use a SQL query to compute just the scalar, but the query in parentheses has to make sure that it delivers exactly one column and exactly one row. Such a subquery, a scalar subquery, will be converted by SQL to us in a scalar, and that could be inserted as one generated column, as the lex column, by the way, in the select clause. So how do we do that? So okay, so we will iterate over the information in the bodies table. So recall that there are only two rows there, the row for the 2 and the 4-legged animals. Okay, and we will order these two rows. We will order these two rows based on the difference of the shape difference. The shape difference for the entry in B and the shape difference for the dinosaur D that we've just computed. Okay, so recall that, or see that this is a correlated subquery. We are referring to the row variable D at this point, and at this point it's a free variable from the viewpoint of this particular subquery, but D has been introduced on the outside in the enclosing query, so everything is fine. Visibility of D is a given. Okay, so that makes sense. All right, so we are computing this shape difference, and the order by will order the rows of the bodies table in increasing shape difference. So the bodies entry with the least shape difference, the least difference to the shape of our dinosaur D, will come first in that order. And exactly this row we will pick. Everything else is going to be ignored. We will pick the row with a minimal shape difference. This is what we pick, and its legs entry is our hypothesis for the locomotion of the dinosaur D. So this will produce a single column table, and it will produce a single row table. And this is exactly what we need for a scalar subquery. All of this will be converted into a scalar, the number of legs for our dinosaur D, and yeah, we can just union that with the information of the dinosaurs D for which information is known. This will be the entire implementation of our plan and the answer to our query. Okay, so let's mark all of this. And execute it. And that's what we see. That's what we see. Let me enlarge this a bit. A fully specified dinosaurs table in which the mode of locomotion for all of the entries is either known or has been inferred. So let's check. So for example, I remember from Jurassic World the Compsognathus, these teeny weeny mean creatures. Our inference says that it has 2 legs, and I brought a picture of Compsognathus. Yes, 2 legs. Looks good to me. Using 2 legs for locomotion. And there's also Supersaurus. I think Supersaurus or Ultrasaurus. Ultrasaurus has been unknown before, and our inference has inferred it to move with 4 legs. Here's a picture of Supersaurus, and I think that's perfectly okay. The inference is perfectly fine. Okay, very nice. So that would be a use case for the with construct, a common table expression that relieves us from thinking about the details that have led to the computation of the bodies table. This is just one temporary table named here in this common table expressions, but you will see that further examples will use a quite extensive number of these common table expression defined names to build up query logic step by step and to have some modularity in the formulation of SQL queries. Now, as a final point, as you've seen here, we have been using order by and this limit 1 to identify one body's row among other rows, namely the particular row whose shape difference was minimal. And identifying a particular row among a group of other similar rows, that's also a job that could be formulated using the distinct on clause that we have discussed in earlier videos in the course of this chapter. So what we could do is we could find an equivalent formulation of the whole thing without the limit clause, but instead using the distinct on clause. And I think that might even lead to a nicer, even more readable formulation of the whole thing. So we would just leave the bodies query in place here. This is a nice piece that you can build on, but the rest of the query, the top level query of this common table expression, I would like to replace with a distinct on formulation. So let's see. Whoa. Okay. All right. Now I recall. So I would love you to formulate this alternative query of the dinosaur shape query that would deliver the same result as our limit 1 formulation above, but that would rely on the distinct on clause instead of limit. So no limit, please, in your alternative formulation. And I'm looking forward to your solution that you are posting to the Advanced SQL forum. Looking forward to that. So much for chapter 02, the core of SQL in this advanced SQL course. We've done it. We are through this chapter 2, which is one of the bigger chapters, and that also makes the way free into discussion of the more advanced and more maybe even more interesting features of SQL. I'm looking forward to that. I hope you stay tuned and see you then. Bye-bye.